Hello. Hi, everyone. Welcome to this great lecture by Alessandro that we're going to see and listen now. It's great to have Alessandro here with us. He's been participating in a couple of events with the RDF Lab. This is actually a collaboration with the RDF Lab and presenting Alessandro's lecture today to everybody. He's been, you did a part of a workshop online and now here in person in the lab. I'm going to pass the microphone to my friend and colleague, Pavlin, who's going to introduce Alessandro. She's going to do a better job than me. And then we'll go from there.
Okay, thank you. So, Alessandro Zomparelli, where do I start with his contributions? I mean, come on, he's done a lot of work with Blender plugins, add-ons, and he's been also part of conversation with us in the RDF lab for almost 2 or 3 weeks now, with first setting up the workshop and now conducting it. So Alessandro is currently working as geometry engineer at AI Build. For those of you, if you remember, AI Build kind of is one of those companies that were the pioneers in large-scale 3D printing, like really pushing the boundaries of what one could do with 3D printing, from pavilion scales to facade systems and all. And I think Alessandro's contributions are only an addition to what our possible futures with 3D printing could be. He was also part of Southern Denmark University as a research fellow for almost 3 years, from 2020 to 2023. And currently, he is continuing to develop open source Blender add-on, and I believe he'll be discussing a lot about it today. So let's see what the possibilities look like for our future with 3D printing and softwares, right?
Thank you. We use this. Can you hear me well? Okay. Hello, everyone. I'm Alessandro Zomparelli. I am a computational designer, and I am currently senior geometry engineer at AI Build. And as we were mentioning before, AI Build is a software company that develops solutions for large-scale 3D printing. We started working on this project in the context of architecture, but then we realized that the same principle, the same technology can be applied to many different fields. So now we are working really on any type of fabrication that requires our large scale usually, and not anymore only 3D printing, but also CNC milling and other processes. But in this lecture, I would like to talk more about my previous works and the works that I'm doing in parallel with this work with AI Build. And the name of the lecture is Topology and Beyond: Computational Design from Human Body to Complex Structure, because I want to mention a little bit about the topology, the concept of topology in design. And the thing is that in different contexts, topology may trigger different concepts, different ideas. And I think it's interesting to see how topology moves from the data structure, the information that you usually use in designing, to how you actually produce the 3D geometries that then are going to become design, but also the geometrical properties of the object that you're doing, but it also transfers to the fabrication as well. So working consistently with the topology allows you to actually stream through the different phases of the design and being effective in that. And I would like to see how in different projects topology has a different role. So I work on many different projects, different collaborations, and my background is in building engineer and architecture. So I initially started to experiment a lot with experimental architecture, seeing how digital fabrication can bring different advantages in the context of architecture, doing some experiment. But then I moved also to other applications in general, to design related with the human body, for example. And from there, other application of design, product design, and other different applications that are always linked together through a digital approach to design and also a digital fabrication technique that most of the time happens to be 3D printing. And also, while doing all of that, all the experiment that I'm doing, all the research that I'm doing, something that I also bring on the teaching side. So I like to travel and do workshop in different schools, experimenting and stressing a little bit the concept of what I'm experimenting in my practice. And the first project I want to show you is called Emergent Reef, which is actually the project where I started to experiment and familiarize a little bit with computational design. This was my thesis project during the master, and I discovered about computational design thanks to Alessandro Zomparelli, which was my professor. And the idea was to develop a system to help preventing and reduce the phenomenon of the coastal erosion. I think it's something you're quite familiar here probably with this topic. I think it's a hot topic in Florida and Miami as well. And the idea is that to build an infrastructure that help reducing the coastal erosion. And as you can imagine, in Italy is a quite spread and relevant problem. It involves 669 kilometers, which would be translated in 416 miles. And the idea was to create a system of barrier that help reducing the impact of the waves on the coast. But at the same time, when you start building something underwater, this becomes also an opportunity to create a substratum that can help the development of a marine environment. And by doing that, of course, you create something that is effective for a touristic application, which brings money that you can use to finance the structure, and then you create this positive and nice feedback that just support this type of development. When you think at a material that you want to use in that context, there are many different options actually. Most of the time, traditionally used probably concrete. You can use stones. There are more experiments using different type of materials. But I think that a very nice application that we found is that you can also use sand, which is coming from the environment itself. And the idea started from this company, which is called D-Shape, and they developed a technology to print stone. And to print stone, they use sand. They put together a couple of chemicals that are based on magnesium, so nothing super strange, just salt, basically. And with creating this printer, they lay a layer of sand with some additional chemicals. Then on top of that, they pour with a binder a composition of magnesium chloride. And as you can see, there are all those tubes. All those tubes, they represent nozzles that are gonna drop some drop of binder following this matrix grid along the sand bed. And by doing that layer after layer, you manage to basically reproduce a large-scale 3D printer, similar to what can be used also on a desktop printer. So the idea is that you combine different layers. According to your geometry, you pour the drops of water in different regions. And this provides you at the end a volume of sand that you can remove, and you can extract the final piece. The nice aspect of this workflow is that all the sand that you are not going to use, meaning the sand that didn't touch the binder, stays there and acts as a support for the next layers. So this allows you to have quite some free-form expression in what you're doing. You're not constrained by the gravity while printing. Of course, the final piece should work structurally, but you don't worry about that during the process. So I tried to figure out what was the best way to approach the design using this technology. And what I thought is that, okay, the 3D printing itself basically follows a grid, because we have different layers. Every layer is following a grid of dots. And this reminds me of a modeling strategy that you can use, which is called the voxel-based. And it's very similar because you have a grid of voxels, meaning volumetric pixels, just small cubes. And you can use that to model something. So this creates a nice correlation between how you're going to fabricate an object and how you're going to model it. The nice thing is that this is not just about how you model it, it's also about the processes that you can use for modeling and the information that you can also embed in any of those voxels. And for example, when you have to work on underwater structures, it makes sense to, for example, inform the design based on some fields of information, like the direction, the intensity of the currents. All those data, they can be mapped to the voxel that we have seen, and they can inform the design. And together with that, you can also deploy some generative strategies that takes advantage of this correlation between the voxel inside the grid, meaning that you can reproduce some strategies that kind of similar to what happened in the finite element analysis, but developing something more generative. For example, this reaction diffusion pattern. Reaction diffusion pattern is quite popular at this time, but what was interesting for me is not that just it looked like the pattern of fishes. That wasn't the reason for using that, is that it created this alternation between void and the structure that for me was relevant for the type of design that I wanted to achieve. So I started to play a little bit with the mathematics behind that. I developed some sketches to simulate it and to parameterize according to the most relevant parameter. And as you can see with this simulation, you can achieve a wide range of different patterns, different possibilities. They all have some trait in common, so it means that there is a specific language, but also specific type of feature that you can get. And what happened is that in nature, basically, this is governing the type of pattern that you see in most animals and the fishes, and etc. So I started to do some experiment. I saw that there was potential, and tried to see what were the effects in different conditions with different type of parameters. And I had to study how it was working in order to being able to bend it and use it for the design that I wanted to create. And I started to also introduce a directional field. So I wanted to make something that was working in the context of the marine currents, but also to use it for some specific design purposes in order to drive the walls that I wanted to design towards specific directions. And I figured out how to control the direction of the reaction diffusion as well. And I started to apply to some data from the context, some other input that I was using to controlling it. And the thing that you see here are basically some possible layouts of underwater walls. And the cavity that you see is where a scuba diver can go and actually explore the landscape. And the darker part are the structure, the reef that I was planning to design in this specific point. And having this extremely flexible generative strategy allows me to actually experiment a lot with the topology of the object, because you don't have to predefine what is going to be the structure of the object. Something that emerges with a lot of freedom by playing with the different parameters. And for me, that was a crucial aspect of the design exploration. I really didn't want to constrain in any way the design. I wanted to see all the possible strange results that I could get from that. And as you can see, for example, this is a small underwater hole, we can say, with the different walls and the currents that pass through that. And the next step for this design was to apply the same pattern with a smaller scale in order to articulate a smaller texture in those walls. So by simulating the reaction diffusion at a smaller scale, what before was a channel for scuba divers to go and just a system of walls became more a texture in the material to host different organisms, different fishes. So the pattern tends to produce a system of cavities and structure that can work with as a substratum for the marine ecosystem. So here you see a simulation of how this is generated, and slowly it converges to a final configuration, which becomes the actual design. So this is a very old render. And these are some of the small prototypes that I was producing, where you can actually see the two different resolutions. So you see the system of walls, and at the same time you see also the system of cavities of pattern. And I think what is interesting for me in this project is that using the reaction diffusion, I was able to have a very high level of complexity of the topology of a geometry. And by saying that, I mean that I was able to produce a topology with a very high level of porosity and cavities, something that I didn't have, of course, to design manually, but I could just inform using fields and information from the context. And this project evolved a little bit. So together with a larger team, we managed to design a small prototype for the actual production and testing the fabrication with the technology that I was mentioning. So we printed one of those pieces, and what we realized after printing is that you actually have to remove all the sand. So this was a part of the process that we didn't really realize before going there and actually start cleaning it. So this is the cleaning process, and this is the final result. And As you can see, this allows quite high level of freedom of the complexity of the shapes that you can achieve. So I think that this is the thing that for me was more interesting, and that's why I wanted to kind of maximize the complexity of the geometry just to stress and test this property. This is, of course, something that you cannot produce easily with a subtractive approach or a different deposition method. And after this experiment, I started a collaboration with a colleague, Filippo Nassetti. We created a research group, which is called MHOX. And the word starts from the HOX genes, which are the genes responsible for the morphogenesis of the body. And that was just an interesting way for us to start experimenting with the same digital logic that we were just bringing from architecture to the human body. So the first project is this system of masks. And we were working in this case on both the software development and the design development. And we were kind of trying to understand the balance between the two and the intersection between the two. So we created a software that was handling a 3D scanning process using a Kinect sensor. And we were developing some tools to achieve a specific design. So we were drawing those curves, and then a simulation of bundling algorithms were connecting those curves, generating a geometry that then we were sending for printing. And the technology that we were using is kind of a smaller scale of what we saw before. So you see a powder printer and a selective laser process that with the laser just melts the material and allows a high level of complexity of the geometries. So these are some of the products that we design. And again, in this case, we wanted to take advantage of the possibility of this 3D printing technology to try to experiment with a language of design that is a bit far from what we are used to. Because usually most of the products that we have, they are coming from different processes like injection molding, a different fabrication method, more industrialized, so something that has been optimized for lowering the cost and maximizing the efficiency of the production. And this type of technology allows to experiment with something else. So we wanted to experiment with both the adaptation that justify the use of a process that is not standardized, and also to increment the complexity of the aesthetic and the type of geometry that you can produce. So those are some of the images of the designs. And starting from that, different research branch started for our project, and we applied that also to different medical products. For example, some orthoses for the hand, that are devices that are used for support some feature of some patients according to the different conditions. So we develop a system for the hand and one for the leg. This one is currently under development. This is an early stage of the process of the project. Now the design is a bit different, but this is an ongoing research. Similar project, similar to the mask, is this Carapace project. And in this case, we took inspiration from the microstructure of the exoskeleton of insect and crustacean. And what is happening in nature that is interesting is that nature usually trying to find a way to optimize the amount of material that is used in some structures, because there are some resources that are a bit scarce in nature. One, for example, is energy, meaning that you need to have protection that is lightweight to carry. You don't have to spend a lot of energy to carry it. And at the same time, material. And both, they come from food, which is a scarce resource. So in nature, you find a lot of optimized structure that are really interesting to study and to use for design purposes as well. So we reproduce an algorithm that was kind of recreating similar properties. And here you can see how this change in porosity, it creates openings and a more stiff structure. And the idea was to inform the design according to some input parameter, input fields that were defining this property. For example, in this project, we created a mask, and we created a field that was creating more openings in the site area and more stiff regions in other parts. This is, of course, an artistic project. It's part of an exploration of a specific aesthetic. It was a research about different levels of design interaction with the human body. And this is the first mask, and this is the second one that replicates something similar but covering the earring side. And the same type of research has been applied to another project in collaboration with Enea, with Shiro Studio, the Enea project. And in this case, we applied that to the design that he was developing of a walking stick. And what he wanted to do, he wanted to create an aesthetic of a walking stick that is not the classical stick used by older people. He wanted to create a more contemporary design. And together with that, he also wanted to characterize the inner structure of the design using a texture that was resembling the structure of the bones. And what happened in the human bones, but every bones, is that basically, according to the load of the bones in the different region, the density of the bone structure tends to intensify or deteriorate. So in this case, we ran a structural analysis of the walking stick, concentrating the maximum amount of material in the most loaded part, lightening the other part that were not subject to that level of load. So here you see some of the details of a texture. This is not something that you see in the actual product. It was just part of the inner structure that was hidden. Okay, so those projects that I show, they are kind of working with a high level of complexity of geometry, which is something that is coming from the opportunity given by the 3D printing technology that we were using. In this case, I was doing the opposite. I was using a 3D printing technology which is extremely limiting. Because when you print with clay, basically, the gravity has the biggest role of all. And what you do, you have to work with a very simple topological element, which is just a continuous curve. So you have a design that at the end is going to be translated in a continuous spiral or a system of curves, and this is the path that you're going to follow with the material for the deposition. So in order to have an interesting design, you have two options. One is you make an amazing model, and then you slice it with very thin layers so that you don't see them at all, or maybe you kind of hide them. Or you say, okay, this texture is part of the technology that I'm using. So instead, I show them as much as possible and make them as part of the expressive design that I'm trying to do. So in order to do that, you have to have a higher level of control over the curves, and they become actually part of the design. So the curve that you use is not anymore like a tool that you use for bringing your design to the fabrication. It becomes actually the design that you're producing. So to do that, I developed an add-on for Blender. Blender is an open source software for 3D modeling using animation and a lot of things. And I created an add-on that allows to take some curves that you can create in Blender, and then you export them as a format that is called G-code, which contains all the information that you can use for the fabrication. And with that, you put it in the 3D printer, and then you can print your object. So what happens is that you can do something that is not something that you're supposed to do. For example, you can deposit material without any support, generating some shapes that are actually coming just from the behavior of the material itself when there is lack of support. So this allows to experiment with something that otherwise would be difficult to achieve by just doing a normal slicing, where you have a predefined geometry and you just slice it horizontally. So this opens a series of new possibilities of the design. So probably you have seen similar experiments around. I think it's one of the common languages that you see when you play with clay printing. So nothing super innovative on this side. But I like the idea of embedding those features in a modeling software that kind of empower a lot of people to experiment with something that otherwise could be a bit more tricky. So here you see how the material create this pattern, and when you control it with some gradient images, whatever, you can make it as part of your design. And in this project, I was collaborating with Bruno De Masi, which is a computational designer, but also a ceramist. And the nice thing is that he was knowing really well the material and also the processes that you can do with the material, for example, the glazing. So in this case, what we did was to use this white glazing that was kind of almost hiding the layers where it was smoother, but emphasizing a lot the texture when we had this kind of extrusion of material on the outside. So we were triangle playing with this transition effect. On the other side, we played with different glazing techniques that instead were highlighting as much as possible the layers. So the topology, this continuous path and the pattern that is creating is visible not only as a 3D texture, but also as a color. So it's interesting because when you start entering in this world, you realize that there are a lot of interesting possibilities to play with that. We really just scratch the surface because there are so many things that you can actually try. This is a detail where you can see the color, how it tends to hide in between the folds of the material. In this case, this is a project, a collaboration that we did with VCU in Qatar. And we wanted to play, in this case, with non-planar layers in order to create a smart block that has this peculiar shape, which is kind of looking as an hexagon when you look at the front view. And we wanted to play with non-planar layers in order to have a texture that has this level of coherence with the design. So for us, it was important to have this level of relationship between the different steps, so that when you combine together with the different component, this texture becomes actually part of the design. Again, it's not just a layering that is just part of the technology that you're using, but you use it as part of aesthetic, the design that you are creating. This is an evolution of the same system of blocks. This is inspired by the mesh rabia, which is a porous brick structure that you have in a lot of Arab countries. And the idea was to play with the porosity, the transparency of this system of bricks. So we created a design with different level of openings in order to achieve different level of transparency, opacity of the wall. So here you see just a render of how it looks, for example, in this case. And with different designs, we were achieving different level of porosity of the structure. And we printed a few sample walls that have been exposed in the expo in Qatar. Okay. While doing all those works, all those experiments, I mentioned that I was developing also some add-ons. I mentioned that I'm kind of working on the design aspect, but I'm also working on the software aspect of some project. So I started to collect a lot of scripts, a lot of strategy that I was playing with, mostly for fun or just for experimenting, or maybe because I had to do some work for a client and I had to develop something. And I started to collect them and I share with the community as an open source add-on for Blender. So the idea was, first of all, if for me something was having a potential, I didn't want to constrain to what I was able to do with this tool. I wanted to empower other people to experiment and stress the strategy as they wanted. And at the same time, I also wanted to kind of promote the use of Blender, that is an open source software with a lot of potential, and I wanted just other people to enjoy the possibility of a free tool that was not really used a lot because a lot of people were just sticking to more commercial softwares. So, of course, I started to develop something, for example, the reaction diffusion that we already mentioned. And the idea of having the reaction diffusion inside an animation software is that you can use not only for design purposes, but it can also use for creating visuals. So I started just to play a little bit with that. this design is that it was actually used as an input for the development of another project, which is this 3D printed cloth made in collaboration with 3S4, which is based in New Jersey, and in collaboration with Stratasys. So Stratasys developed this 3D printer that is able to print on fabric. I mean, it's just a printer in general, but the fact is that it works well when you put some fabric in the printer and you print some patterns on top of that. So it's something that is getting used a lot in fashion design. And the interesting thing is that you can print some patterns with different colors, different consistency. You can play with kind of flexible material, more rigid material, transparency, different colors. But there is usually a specific thing that you have to keep in mind, that as you can see from those printed patterns, you tend to print elements that are disconnected to each other, because otherwise your material is not flexible. So in order to allow the flexibility of the material, you have to keep them separated, which kind of looks like the pattern that we just saw in the animation. So I say, yeah, we can do that. And 3S4 started to work on the design of the garment, doing some paper models. We were defining those shapes that I was supposed to use to inform my design for then going to 3D print. So I used them as input for generating a reaction diffusion pattern, and I was just taking some information from the geometry to inform the generation of the pattern. So for example, here you see this external boundary is used to create a gradient. So I wanted to have a direction spreading from that. At the same time, I wanted to make it a little bit more dynamic, giving a small angle that was creating this twisting effect of a pattern, and this is a representation of a reaction diffusion pattern that is generated in this case. So here you see just the interface in the software of how the pattern looks and how you can correlate with a node system, for example, to something more complex to inform the different extrusion level of those small triangles. And here are some of the geometries that I was producing. I wanted just to express with a different feature of the pattern, trying to achieve different effect and to use, again, the direction that were coming from the shape. So Stratasys was printing the samples. This is just a detail of one of the printer where you can see clearly the extrusion. And we wanted to have this transparent effect at the base, and then having this more opaque color on the upper part. Then 3S4 started to stitch together everything and combine them for making the garment. And you can see that there is also the possibility to create these color variations. So we were playing with different gradients, different colors. And this is the final piece where we were putting together all the parts. So I mentioned the tissue add-on, which is something that I developed. It's something that I use a lot in my workshop because just help working on some design principle, trying to get rid as much as possible of the complexity that comes from actually doing all the technical aspect of the modeling. And probably the most famous feature of this add-on is the tessellation, which is a very basic principle. It takes advantage of how mesh modeling works. I don't know if you ever use mesh modeling, but basically when you model a mesh, your geometry, which in your head tends to be continuous and smooth, in reality gets subdivided in different phases. Those small phases, they can be seen as a low resolution, like a loss of continuity of the surface, but they can also become an interesting system of panelization and discretization of the surface. So usually they have a quite interesting correlation with the shape that you're trying to do. It's just not a random tessellation of the face or of the surface. And when you work with those software, you can easily get some nice control over the distribution, the pattern that you can create with those geometries. So with the tessellation, what happened is that you use this topology of the mesh to replicate a component and get a pattern that is the combination of all the components following that information. So for example, you see two similar surfaces with different level of subdivisions, and when you apply the component, you get two different type of pattern. This is a very simple component just to showcase that principle. But the nice thing of having that inside a modeling software for animation is that people start also to being interested in different application. Of course, it's coming from an architectural background, but it's also interesting to experiment with other type of design, just to explain to people that are not coming from architecture what would be to design with this approach. So you see that this complex design is actually coming from the topology of this surface, where the different colors are associated with different components, and just creating those directions allows you to create some feature that just comes automatically from the process. Usually when you want to model something like that, it may require a lot of manual modeling operation, where you have to manually go there and do some extrusion or something. Here you decompose the complexity in the smaller ingredients, which are just few components, very simple to model, and then you apply them to the final surface. And the same process is something that I'm using for other projects, for example, medical products, where the different feature of the device follow a similar rule. For example, here I was producing this device for this little girl, and we wanted to create the shells that can be open, having this seam between the two shells. And instead of doing some manual modeling, I say, okay, why not just creating a component that contains the connection between the two shells? So I do the tessellation, and then I can just open the file and have the two pieces separated. And of course, some architectural application. This is a fun one, because we did this workshop in Saudi Arabia working on metaverse architecture, so it's just whatever you can do, it's fun. And we were playing with the tessellation, doing some just crazy shapes for fantasy architecture. But here you see, for example, that you can apply that to different scale. For example, if you imagine that kind of floor, wall, and ceiling is a component, when you apply radially, you can create like a column object. But when you apply to a more complex base geometry, then you can create a system of columns. And everything comes just from a single component. So you can just do some changes there and see different possible outcome. And when you see that, then you can say, okay, why not applying another texture to that one as well? So you can create a component, apply to that, get a different result, and you get this. And at the end, the actual modeling that you did is very small, because you did just a couple of components, and all the rest is just propagation from that. So you see a video of how it was, for example, during the workshop to model on something like this. So the idea of the add-on itself is to really get rid as much as possible of the complexity of trying to translate a design idea into this thing, and just rely on very basic modeling tools that you have inside the software. And then we were creating those architectural objects. We were uploading them online and doing some real-time navigation. Okay. This is a project that I did in Denmark, in SDU University. And we were bringing the same principle that we have seen applied to very abstract architecture or objects that are a bit more close to product design or animation design. We were using that as actual fabrication method for this polyhedral structure. This is a research that is starting from a previous research on the complexity of polyhedral structure and their role as efficient concrete structures. So they are kind of coming from a different loading condition, studying how the forces are actually designing this type of efficient structure that they are quite interesting to study from one point of view, but at the same time, they open a lot of challenges in terms of fabrication. So the problem was to actually find a nice way to produce this object. So there are several projects that use this type of modeling approach. But what we wanted to do here was to create a structure that can be used to actual application. And using that, we wanted to use concrete and an internal steel structure. So what we wanted to do was to have a system of components. We see here that we were producing those 3D printed elements that were keeping in position a system of reinforced bars. So on every face, on every end, we have a steel plate that have a bar which is welded at the base of a plate, and then they are positioned in order to allow a person to weld at the center. So you see here a detail of the different bars that are converging to the center, and this system of arches of 3D printed element, they create enough openings for an operator to go there and actually weld the bars. So here you see the operator welding them. This was used just for the picture because in reality we have to cover them in order to prevent them to melt because of the heat that it was producing. And then we were printing some shells made in PLA, so it's just the common material that you usually use for printing. Those shells were part of the formwork that we wanted to use for casting the concrete, so for pouring the concrete. The pattern that you see here has two functions. I mean, it's an ornament that we were using for the design, but at the same time is also a stiffening strategy for the shell. Because when you pour the concrete, it starts to apply a lot of pressure and it starts cracking the shells. And we wanted to reduce the amount of material that we wanted to use for the formwork, so we were trying to reduce the material by achieving these corrugated surfaces that were kind of acting as reinforced surfaces. So we were putting together the shells to create the formwork, and this is the final formwork with all the bolts to tight everything. The plan was to reuse every shell for 3 different nodes, so the idea was to being able to open the formwork and reuse it 3 times. Sometimes it worked, sometimes it didn't. And this is the final piece. And what is interesting for me is that all the features that are visible here are actually telling a little bit of the story of how the formwork was working. So you see the grooves that are following the direction of the holes for the bolts and the nuts. They are the arches that we saw in the first picture holding together the plates. And the corrugated surface is actually coming from the reinforced shell that we were using. And this is the formwork in this view, where you see all the different parts that work together. So this is a complex formwork to design. And if you think at the picture of the structure that we saw at the beginning, it becomes quite difficult to approach this level of complexity for all the different nodes and all different components that you can have. So in order to simplify the modeling process of this, actually in order to reach this level, what we used was a tessellation strategy. So you see that the node, this single component that you see in the corner, has certain faces that are following certain direction, which are coherent with the pattern that you saw and the grooves that you saw in the model. And we classified them in different types, so the different letters are referred to different components that you see here. So 2 different components that combine together define the connection between the shells and also the underneath arch that was used to keep in position the bars. And that other component instead just contains the corrugated surface and the surface of the concrete. The surface of the concrete is not something that you really need in the model, because at the end you 3D print the other parts and the concrete is just material that you pour inside. But for us, it was important to visualize it because we were designing together all the 3 elements. So we wanted to design a formwork, but with a specific outcome in mind. So the concrete was used as a feedback, visual feedback, to understand the final design that was affecting the choices about the formwork, and then also the formwork had to be had to work for its function. So we had to keep an eye on all the aspects before converging to the solution that you actually saw. And to achieve that, it was important to have a certain level of control of the topology of the geometry. Because when you see those structures, most of the time they come from maybe a modeling approach that is very flexible, that use like voxel-based grids, which are super nice, but at the same time, they create a topology of a mesh that is unusable for this specific purpose. You can try to clean it afterward using some strategies, but they usually don't work perfectly. So we had to work with a different modeling paradigm in order to achieve exactly the topology that we needed. And this, while working on that, became also part of the tissue add-on. So it became something that is available open source. This is a small portion of the structure that we finished to assemble, but I'm not allowed to show the picture because it's still an unpublished project. So what I can show are just some renders of the structure that show a little bit how it should look. And this structure is also supporting a slab on top of that, which I can show briefly. Again, we didn't publish properly, so I cannot show too much about the process of doing that. But as you can see, there are some specific directions that are following the direction of the stress with a certain loading condition. And we were organizing the material in order to have a maximum efficiency of the used material for this specific design. So I cannot show a lot of things related with this specific design, but the last project that I want to show you is kind of describing something that is kind of similar, which is the RD Slabs prototype, which is a project that we developed during the summer school in Denmark. And RD stands for reaction diffusion, of course. So when you have a structure in general, you have this field of information, which is the stress that is produced by certain loading conditions, certain support system that you have. And this usually is made of direction. And if you want your design to work effectively with those conditions, then you will tend to orient the material that you have according to the direction of the stress. And this usually produces some more efficient structure that has been experimented a lot in architecture in the history. But the problem is that when you just convert that directly using the digital tools that you have, you tend to get these streamlines that they converge and they diverge in a very unpredictable way, and they cannot easily be used directly as design input. There are some strategies, but sometimes you always have to pick a little bit hand by hand what are the trajectory that you want to use. So in this case, we say, okay, why don't we use the reaction diffusion pattern that have already some embedded properties that we already saw can be used and driven by a vector field. And again, the separation of elements that we have, they can act as stiffener in a slab structure. So here you see an implementation of the reaction diffusion. In this case, I made a small change. Instead of working on surfaces, I was making it working on 2D textures, because this was allowing easily to use other 2D texture as input for controlling some features. For example, the direction of a pattern, the scale of a pattern, different properties. So this was just a simplified interface that was allowing the students to use a strategy that could be a bit complex to control, but to simplify as much as possible the workflow, the process for them to use it for the design. So here you see two different designs, so two different systems of support with loading condition. They are generating different input maps that contains the direction of the vector, the intensity of the vectors, and also the sign of the moment vectors. And they are used to drive the formation of the reaction diffusion pattern that works with those specific designs. So you see the two patterns. At some point, they start to converge to a final configuration. And here you see the vector field with different maps and the design that is produced out of that. Of course, you see just an image, but then you can use the information of the grayscale image, giving thickness, variable thickness to the structure, and combining that in different ways. And this type of object is produced with concrete, but before that, we had to mill a styrofoam block in order to have a formwork to pour the concrete inside. And in order to do that, you also have to take care of something else. Similarly to how you print clay, in this case, you have to think of what are going to be the trajectory for my robot to mill. You can just use it and just generate automatically a lot of parallel lines. It works, but it takes a lot of time. And during workshops in particular, time is not really something that you have in abundance. So we wanted to optimize as much as possible the time for milling every one of the objects, because every hour we're really counting. So we were using different strategies to use a low resolution milling strategy, but still having an effect that was making sense with the design. So after doing several tests, we realized that when you have a pattern, like the reaction diffusion, when you add another pattern, which is basically the milling path that you're producing, they can generate some interference. And they can affect the aesthetic also of the final object. So you can see that sometimes they align nicely, sometimes the alignment are not great, like in this case. And in this case, they were producing some strange results. So we realized that the best effect was when the milling path was perpendicular to the reaction diffusion pattern. So in some of the tests that we did, we were actually using also the reaction diffusion pattern as an information of how the milling path was actually working. So you see that here is just jumping left and right, following the reaction diffusion pattern in order to create a pattern that was low res to save time, but at the same time was kind of creating an interesting effect according to this specific design. This is the formwork after some coating and putting some reinforcement bar that have been banded using some mixed reality visors. And this is the final result of a pour concrete. So this is one of the two slabs where you clearly see that the reaction diffusion pattern tends to propagate from the support that you see in the corners. This is the same design, and this is the other one, where you can see how the milling path is always perpendicular to the reaction diffusion pattern in order to create this coherent language between the two systems. So yeah, I like to finish with this project because it's one of the most recent ones, but also because it combines together different things that for me are interesting. So the architectural research, the add-on development, because this is part of the project that I'm developing and I'm spreading with the community, and also the teaching program, because I like to just work on those things with students and collaborate with people. Thank you.
I think, yeah, we can start with the questions. Question? Or okay.
I absolutely love how not only do you make beautiful things, but you also share your knowledge and empower others to make beautiful things by releasing your knowledge and tools that other people can use for the open source community. If you can remember way back in time, before you gained all that knowledge, can you talk a little bit about how working with an open source tool and an open source community helped you learn and gather this knowledge, and maybe give some advice to students for some successful strategies for how to learn this really advanced stuff when there's no roadmap for it?
Yeah, probably there is no roadmap for that, not that I'm aware of. But for example, in general, I was enjoying a lot the use of digital tools. So for me, was part of the fun of the design process. So I was liking the design, but also understanding how the different tools were actually opening different opportunities for the design. And for that reason, I remember that every exam that I was doing at university, every test, I was using a different software because I just wanted to jump from one to another. Because the fact is that the use of a digital tool is something that empowers you, but also defines some constraint for you. And you can deal with the constraint and just accept that, and that's fine. But sometimes you just want to extend as much as possible those constraints. So that's why I started to experiment with different tools. And during the process, at some point, I discovered open source. My brother was a programmer, so probably this has had an impact. And I realized that, I remember that the first time I tried Blender, it was at the early stages, so it was really underdeveloped compared to how it is now. But what surprised me is that I remember I was using 3ds Max, and I was opening, then I was going to take a coffee, I was coming back to the desktop, and I was starting using it because it was still loading things. And at that time, Blender, I think, was like probably, I don't know, 7 megabytes. And it was opening like the calculator in Windows. So you just open it, it's there, you can start modeling. You were lacking a lot of features, but I was liking this aspect of that. And also, the software itself was designed by the users. So it was really adapted to the needs and the requirement of the community. So you start understanding a little bit about that and the fact that a lot of companies, for example, they started to switch to cloud-based systems that have a lot of advantages. It makes sense for some reasons, but at the same time, they keep some ownership of what you develop, of what you do. So you have to think, okay, I'm a designer, I design things, but do I own the things? Do I have the power to control the design if a company makes some changes in the policy for releasing the licenses, or if some functionalities will disappear? So you start questioning those aspects that, of course, you can just ignore them. As many things in life, you can just say, okay, whatever, I don't care, it's going to be fine. Probably it is. Or maybe you find it interesting also to understand that there are other possibilities. So I got excited about open source, and when you start doing some code yourself, then you just say, okay, it just become natural that this also become open source, because I use open source tool until now. And so yeah, just for me, it was making sense.
I think a nice thing too is that you can just email the person who made the tool. So if you have questions about tissue, there's not like you don't have to fill a form to Autodesk,
Yeah.
some engineer. Like you just reach out to Alessandro through GitHub, DM on Instagram, or like comment on YouTube, and you're right there with the person who made the tool, and you get to be a part of their brain, a part of their process.
Yeah, initially I didn't consider all the implication of that, because I publish it and say, okay, I just made it open source, and then people was using it. They say, hey, it's not working, I do that. I say, yes, you're not supposed to do that, but you don't know that, so that's a problem. And so that created a lot of different iteration of the add-on itself in order to make it actually usable, to prevent all the strange errors and everything.
I can just project it. First and foremost, thank you so much for creating that add-on. I've used it myself. It is awesome.
Thanks.
I didn't know who made it, but thank you.
Thank you.
Second, I also have a lot of questions, but I'm going to try to be direct here. Have you played around with like the self-printing technology that MIT was experimenting with in like 2018? Because the polyhedral structures, they look very like similar technologies that they could be applicable, and my brain's going now.
Okay, no, I'm not sure I'm familiar with what you are referring to.
2018, I want to say, MIT made these little, they called them fibrobots.
The one that spiralized and okay.
Monofilament and resin, and they
Okay, I know the project. No, I didn't, but that's a cool one.
Because I was just thinking, like, the polyhedral structures, like, do you think that's the future of the technology?
I mean, what I learned from the structure that I show is that this specific process, it's really complicated. And we discovered while working on that. So we were solving some geometrical and technological problems, but I don't think this, for example, would be the ideal solution that you can use and plug and play in every context. The interesting thing of that project is that it's very efficient in what it's doing. So for people that doesn't know it, basically you have this kind of spinning robot that is moving and extruding a pipe while moving along the pipe. This is the project, right? And I think it's a very smart application in that context. Of course, there are other limitations that are coming from that. For example, if you want to make more redundant structures, this becomes a bit tricky because all the structure that I've seen were kind of slender pipes. So I think it's an interesting technology. Probably, I'm not sure if they already find the killer application that makes it particularly effective. But yeah, I think that every time you have to find probably different technology, they have different advantages and disadvantages. Sometimes they work perfectly for a certain application, but maybe they cannot be used universally. So for example, for the polyhedral structure and the redundancy of the structure that you have, maybe this system may have some limitations, but for other structure probably it's make a lot of sense. Thanks. Okay, I've worked just a little bit with Blender Beam because, as you have seen probably from the project that I shared, I'm working more on a smaller architectural scale, working more on the experimentation with the fabrication. I did some interaction with the developers of Blender Beam, trying to understand also how tissue could be connected with that. And I think it's an interesting application because when you want to consider Blender for the real architecture, not just the experiment that I was showing, this makes it a more complete tool. So I think it's a very important thing that they are developing it, and I think it's very promising. I personally don't use it because I just work on a different scale. And sorry, the second question? Okay. Well, there are already some interesting things that are happening with AI in Blender and the stable diffusion integration. And I remember that when I started doing rendering, I was spending a lot of time just trying to set the parameters for the photons to bounce in a certain way, certain amount of bounces in every surface, and controlling all those parameters. So it was really time consuming. I see that probably very soon you don't really have to know anything about render because you just make the mass model of your geometry and you say, okay, make it cool in a sci-fi Blade Runner aesthetics, and that's it. So yeah, but which is very cool because you can focus more on the design, you don't have to spend time on those aspects. For me it was part of the fun, but maybe it's just me that is weird, that I'm weird. But at the same time, I'm worried that this level of empowerment, of creativity, you may lose the contact with digital bricks that are actually making it. So I see that the disadvantage is that a lot of people will become user without knowing exactly what is happening, which is fine because you use the smartphone, you don't have to know what is happening inside the smartphone. But at the same time, you will start to delegate again a part of your creativity to other people that is controlling the algorithms. I don't want to make like anything dystopic or something, but it's just something that we have to consider. It's just happening. Yes?
I was thinking about the question of scale. And, for instance, I was looking back at the Reef project, one of the earliest projects, and for instance, this later project on the cast concrete nodes.
Yes.
I was wondering if there are like any kind of interesting resistances that you find due to scale, like that lead. So because I'm saying this because, for instance, in this project, there's a lot of like hardware involved and modularity involved, unlike say something much more fluid and continuous that can just be made and you see how it will connect, and of course things can be connected. But it seems like in the case of going up in scale, then it becomes about the kind of ingenuity and inventiveness in terms of systems and the logic seems much more focused on the construction.
Yes.
Mechanisms and the creativity of systems for that. There's something very interestingly tectonic about the other elements that are being introduced, hardware, plates and connectors. Maybe you have any thoughts?
Yeah, that's completely true. And for example, yes, I also work on larger scale, and yes, what happened is that, the fabrication process became like the major driver for the design because that was putting most of the constraint for what you were able to do. And that's, for example, why, what is interesting for me in the polyhedral structure is that the same modeling strategy that we use to just create the texture of a structure became actually part of a production system. So for me, it's interesting when there is this kind of coherence between the different steps that in that scale happen to work. Maybe in other scales, maybe it may be more difficult. It really depends on the technology. But yes, when you start going with larger scale, the challenges change a lot. And that's why, for example, we did a lot of experiment with small 3D printing objects because, you can just have fun with a shape, but then, yes, how you are actually producing that is affecting really how you inform the design based on that. Yes. Which becomes also part of a research challenge. So initially I was perceiving that as a constraint, but then I saw that that was actually an opportunity for drive the design in a certain direction.
I think we're good with questions, and of course he's here even tomorrow. Please drop by the lab, bring espresso. We are still figuring out a best espresso to impress him over here, or a Cuban coffee. And please come hang out with us in RDF lab. And thank you again, Shaheen, Luigi, everyone.
Thank you for having me.
Session and bringing him here. Thank you.
Thank you.